Okay, this is going to be part 2 of the video on how to find whether or not a sequence converges. Now, if you haven't done it yet, I would definitely watch the part 1 video because it describes this theorem right here, which gives us the steps that we'll use to try to solve it. And if you watch that part 1 video, you might remember that if you're given a sequence and you want to find out if it converges or not, well, first of all, take that sequence and match it up with a function that corresponds to the sequence at every point. Then we'll find the limit of that function, and whatever the limit of that function is what the limit of the sequence will be, and we'll be done. So those will be our steps. So again, if this definition is not familiar for you, I would immediately stop this video, back up, watch the part 1 video, then you should be okay on this. And also one final comment before we go on. If you're trying to find the limit, or pardon me, the convergence of a sequence, these things really turn in, they're not so much sequence problems as they are limit problems. So the heart of trying to figure out whether a sequence converges or not involves finding the limit as x approaches infinity of some function. So if it's been a while since you've worked with these, I would also back up, and there's 3 or 4 videos that deal with how to find the limit of a function as x approaches infinity. And definitely watch those before you try this, because if you don't know how to find the limit as x approaches infinity, then you really won't have much success with these problems. So review that first. Once you've got those limit rules down, then this will be a whole lot easier. So anyway, with that, let's take a look at a couple problems now. First problem looks something like this. Here is a sequence, and I just want to find out, does it converge or not? And if it does converge, what does it converge to? Now, in all these problems, you don't have to do this, but sometimes I think it helps if you have a plot and see what the thing looks like. You can get a visual idea of what's going on. So first of all, suppose we were to plot these points. So if I were to take this sequence and let n equal 1, n equal 2, n equal 3, and plot them, they would look like this. Now the question is, does this thing converge? In other words, if you go way off to the right, do these blue dots seem to be approaching a fixed number? And in this case, we'll kind of draw a line and show what it looks like here. It looks like, if you put a line here, the blue dots do seem to be approaching this red line. And the value of this red line is, looks like here's 1, here's 2. Looks like it's halfway in between. So it looks like it's going to be approaching 3 halves. And that would seem to be, or 1.5 seems to be the point that this thing is converging to. But we also want to be able to show it analytically. So let's go back to our definition. And again, what we'll do is this. We'll take the sequence and we'll change it into a function that corresponds to the sequence at every point. And then we'll find the limit of that function in terms of be f of x, and it'll give us some limit. Whatever this limit is, if the function and the sequence correspond at every point, then the limit of the sequence has to be the same thing. So again, if you need to, review that part 1 video, but let's go ahead and use this as our guide. So the first step is go ahead and change it from a sequence in terms of a sub n into a function in terms of x. So I'll make this be f of x is equal to, and just everywhere I've got an n, I'll replace it with an x. So 3x plus 4 divided by 2x plus 1. Now again, the reason I'm doing this is I have rules for finding the limit of a function as x goes to infinity, but I don't have any rules for finding the limit of a sequence as n goes. So the first step is to do this part right here. So what I've done is I've found a function that matches the sequence at every point. Now the second step is now we'll go ahead and find the limit of this function. So let's do that. So I want to find the limit as x goes to infinity of this function. And it's 3x plus 4 over 2x plus 1. Now we'll actually do this a couple ways, depending on whether you remember your limit rules or not. And the first one says this. If you're going to find the limit of 2 polynomials, and they're both to the same power, so the power in the top is 1, the power in the bottom is 1, so the limit of the function as this thing goes in is actually just the ratio of the coefficients in front of the highest power. So it'll turn out to be, in this case, 3 halves. So the limit of 3 halves is, and that's going to be what L is. So if the limit to the function is L, then the limit to the sequence is the same thing. So this implies that a sub n, the limit of a sub n as n approaches infinity would also be equal to 3 halves, and you'd be done. So there's the first example. Now also, we'll do one thing here just to show you. If you have forgotten the rules, that the coefficients will give you the limit if they're the same power. Remember, you can also always divide through by the highest power in the denominator. So we'll do one of these, but this will be the only one that we do it on. So this is just a second way of doing it, of finding the limits if you need it. So let's just show an example of this. Here is, the original function was 3x plus 4. And then in the bottom, I've got 2x plus 1. Now remember, this is just a review of limits, but you can always divide through by the highest power in the denominator, which would be x. So I'll divide by x, and divide each term by x. And then what that gives me is the limit as x approaches infinity. And here the x's would cancel out and leave me a 3. Then I'd have 4 over x divided by, here the x's would cancel out and leave me a 2 plus 1 over x. Well, now, if you take the limit as x approaches infinity, anything that's got an x in the denominator will go to 0. So this term will go to 0, this term will go to 0, and you'll be left with just 3 divided by 2, which would give you 3 halves. So anyway, if you remember the coefficient part, then that's fine. If not, you can always divide through. Both of them will wind up giving you a limit, though, of 3 halves. So that's what the first one looks like. And this thing, in this case, you showed that this thing actually does converge to 3 halves. So the question was, does this sequence converge? And if so, what does it converge to? And you can show, using this definition, that it converges to 3 halves. So let's take a look at the next problem. And the next problem looks like this. It's almost the same thing, except that we'll have higher power in the denominator. Now again, let's make a quick plot of it, see what it looks like. If you were to plot this, the points would look like this. So they start, when n is equal to 1, you get a point at 1. N is equal to 2, you get here. And just looking at them, they seem to be approaching the x-axis. So let's put a line on here. If we did this, these things seem to be approaching 0. So as the n goes farther and farther to the right, the terms of the sequence seem to be approaching y is equal to 0. So again, let's go ahead and try this and see what we'll do. Now, we use exactly the same things we did before. First step, change it from a sequence into a function in terms of x. So I'll go f of x is equal to, and I'll make this be 4x over 2x squared plus 2. So that's the function. Now you want to find the limit of that function as x approaches infinity. So we'll find the limit of f of x as x approaches infinity, and that would be equal to the limit of 4 over x divided by 2x squared plus 2. And I want to find this as x approaches infinity. Now again, if you have reviewed the videos on how to find the limit as x approaches infinity, if you got a polynomial divided by a polynomial, and the power, I'll put it in red here, if the power of the polynomial in the denominator is larger than the power in the numerator, then you're guaranteed that the whole thing will go to 0. It has to approach 0. Or another way of doing it is divide the whole thing through by x, the highest power in the denominator, which would be x squared divided by x squared, and you'll get the same answer. So the limit of this thing is 0. So if the limit to the function is approaching 0, then that implies that the limit of the sequence, a sub n, as n approaches infinity, must also be equal to 0. Because the function up here, the function agrees with the sequence at every point. So you show that it's equal to 0. So what this means is this will be converge to 0. So the question is, does this sequence converge? And if so, what does it converge to? And you show that the limit of the sequence as n approaches infinity is equal to 0. Therefore, it converges to 0. So that one converges. It seems to be approaching 0. And let's take a look at our next example. Okay, now in this one, we'll do the same thing we've done before. First of all, the first step, we'll go ahead and change it to a function. So I'll make this be f of x is equal to 2 to the x plus 1. Now in this one, let's actually plot a couple points and see what's going on. The question is, does this function settle on a fixed number or not if you go way off to the right? And if you were to plot a couple points, and let's just go ahead and do that, I'll say when n is equal to 1, or when x is equal to 1, I'd have 2 to the 1, which would be 2 plus 1, I'd have the point 3. So I'll have a point, say we'll put them in blue here, I'll have a point right here. When x is equal to 2, you'd have 2 squared, which would be 4 plus 1, which would be 5. So you'd be up to 5. And then finally, if you had 2 cubed, that would be 8 plus 1 is 9. It would be way up here. So what this function is obviously doing, it's going way off toward a positive infinity. So if you found the limit, here's what it would look like. So you can actually, just by looking at this graph, conclude that the sequence does not have a limit. It goes off to infinity, and therefore the sequence diverges. But you need to show that by doing the following. Let's take the limit as x approaches infinity of the function 2 to the x plus 1. Now this one's actually pretty easy to do because you've got a dominant term right here. And as x goes to infinity, 2 raised to a power will go to infinity. So this term right here would take off to infinity, and the entire thing would go to infinity. So as x gets bigger and bigger, then the function increases without bound, goes off to a positive infinity. Now what this means is that the limit then does not exist. So the limit to the function does not exist. And if the limit of the function does not exist, then also the limit of the sequence as n goes to infinity also does not exist. So if the limit doesn't exist, then you can conclude that this sequence diverges. So if the limit settles on a fixed number, it converges. If the limit does not settle on a fixed number, it diverges. And take a look at another example. Okay, now this is almost exactly the same problem. As a matter of fact, let's go back and take a quick look at this. This one was 2 raised to the n power plus 1. This one is 0.2 raised to the n power plus 1. So now you've got a number that's less than 1, and you're raising to a power. And let's see what that would look like. So if we were to graph it, it would actually look something like this. It starts out about 1.2, and then these are slowly decreasing, and they seem to be decreasing toward this line right here. And what this would be, it looks like, just looking at it, it looks like it would be 1. So they start out a little above 1, and if you take the sequence all the way out, again, visually, it looks like they are converging toward y is equal to 1. But we want to show that. So again, we'll use the same steps that we've done before. First of all, change it from a sequence into a function in terms of x. So I've got 0.2 to the x power plus 1. Now what I want to do is find the limit of this function. So if I find the limit of, as x approaches infinity, of 0.2 to the x plus 1, what do you get? Well, what happens is if you take a decimal number and raise it to a power, that's just kind of, if we wanted to build up a little table here and take a quick look at this one, you've got x, and here would be f of x. Let's make this just be 0.2 to the x instead. So we'll change this to, just to keep it simple here, we'll make it be 0.2 raised to the x power. So what happens if I have 1, I would have 0.2. If I had 2, then I'd have 0.04 and so on. So as this thing goes toward infinity, this part is going to go towards 0. So if you take this and let x go off to infinity, this term right here will approach 0, and all that will be left will be the plus 1. This thing is going to approach 1, and that's going to be the limit. So what that is, that's the limit of the function. And then, again, using this definition, if the limit to the function is L, then the limit to the sequence must also be L. So this means that the limit of the sequence as n approaches infinity would also have to approach 1. Now what that means then is that the sequence converges, and it converges to 1. And that would be a convergence theory. And let's take a look at one last example. Okay, in this one now we've got square roots in this, but we'll still use the same process. So first of all, let's take a look and see what the points would look like if we were to actually plot them. And they look something like this. Now this one, it actually grows very slowly. It goes way off. But if you'd find it, starts here, it will actually approach this red line. So we'll put a line in here. And here's 2, here is 3, and this is right in between the two of them. So it looks like it's approaching 2.5 or 5 halves. So if this goes way off here, if you went off far enough, the blue dots continue to approach the red line, and it looks like this one's going to converge and settle on 5 halves. But let's try it and just kind of run through the process. Now again, first step is change it from a sequence into a function that models the sequence. So it's going to be f of x is equal to 5. Now I'm going to change the square root of x into x to the 1/2 power, divided by 2 times x to the 1/2 power plus 1. So again, using this definition here, we found a function that matches the sequence at every point. Now all we have to do is go up here and find the limit to that function, and whatever that limit is, it will be the limit of the sequence. So the next step is to find the limit of this function. So the limit as x approaches infinity of 5x to the 1/2 divided by 2x to the 1/2 plus 1. Now again, we can use the rule that says if you've got the power in the top matches the power in the bottom, the highest power in the top is the same as the highest power in the bottom, then the limit to the function is just the ratio of the coefficients in front. So this will turn out to be 5 halves, and that's going to be the limit, which is what we were expecting up here. Now what this is the limit to the function, so you've still got one more step to do. So if the limit of f of x is 5 halves, then since the function and the sequence agree at every point, then the limit to the sequence as n approaches infinity must also be the same thing, which would be 5 halves. So the limit does exist, it's 5 halves, and that means that this sequence converges to 5 halves. So that's going to be that. So again, let's go one last step back to this theorem here. And the idea is this: given an initial sequence, find a function, convert it into a function so that the function agrees with the sequence at every point in the domain. Then use your rules for limits to find the limit of the function. And since they agree at every point, if the limit of the function is L, then the limit of the sequence must also be L. But if the limit of the function does not exist, then the limit of the sequence also does not exist. So that's we'll look at a couple more examples in the next video that'll use some additional rules, but that's a start on how to solve these problems.